Okay, as we say the word exponential function, a lot of times our brain obviously goes to thinking about an exponent, which you would see in both of these types of functions, but they are not both considered exponential functions. These are the ones we've been working with a lot recently, but they're called power functions. And x to the third and x to the fifth, those are actually power functions, monomials, polynomials, all of those. When it is called an exponential function, it's actually going to be a base of a number, and your variable is what is up in the exponent, not a number up in the exponent. So just kind of seeing the difference between mathematic terminology for the different formats here, and this is our focus today, is the exponential functions. So if you will grab your graphing calculators, and in your y1 type in that function, 4 to the x, give me a standard window, like a zoom 6. Go ahead and give me a picture of that graph, and then I'll give you a second to work ahead of me, and we'll talk about domain, range, and things that are typical for our exponential functions here. One of the big things that we need to understand as we are looking at this equation or at the picture of this graph is, what should we actually be seeing? And in a non-color calculator, it's a little bit harder to see. So my non-color calculator people out there can kind of understand what I'm talking about here. For a lot of you, it kind of looks like your graph comes up to the x-axis and at some point stops or disappears. And we've kind of talked about this before, and that's where it's getting so close to our x-axis that it's actually hard for your calculator to graph it separately. If you have a color calculator, you can probably see how the line continues on, kind of blending into your x-axis. But guys, it's not actually getting there. So it looks like it's almost disappeared or whatever, but it's sliding along your axis, and then it starts to grow, and then it shoots up really fast. Exponentially fast. It's an exponential growth. So why is it so small? Why is it practically zero over here? If we think about evaluating this function for something like a -3 or a -4, if we were to use our algebra to simplify that, 4 to the -3, that negative would tell us to drop it to the bottom. And 4 to the third is 1 over 64. Okay, if I were to draw the dot 1 over 64, isn't that like super tiny way by my x-axis? So doesn't it make sense that it gets really, it's like a really tiny fraction as we go. It gets to be an even smaller fraction as we go each number over. So will it ever actually be 0 or negative? Think about it. As I keep plugging in numbers here, isn't it going to just keep doing this and becoming a bigger number in the bottom? So pretty much practically 0, but never actually getting there. Okay, so that's going to explain some of our answers along here. But starting at the domain, we can look at the picture and see that it points to the left forever, and this arrow is going the 2 directions, to the right forever and up forever. And so our domain becomes unrestricted, or if you think about what numbers could I plug in this function? Everything. -infinity up to +infinity. Now, we talked about at the beginning how that graph gets really close to my x-axis, but it'll never actually get to 0. I cannot plug anything into that function to make it equal 0. So it's going to get really close to being 0, but not get there. So we show that with a parentheses. And then it's going to head up forever. So our range would be 0 to infinity. Now, before we move on, I want to talk about what's typical for an exponential function. In an exponential function, this will never change. I don't care what you put into this function. It is unrestricted domain always, -infinity to infinity. That will never change if it's an exponential. Your range will be impacted by the function itself. If your graph moves up or down or flips over your x-axis, it will impact that range. Okay, but we'll talk about some other things to look for to kind of help us know that that's at least on the right lines. You have 2 types of intercepts, an x-intercept and a y-intercept. In this calculator section, you guys have calculator functions to find those for you. However, does this graph hit our x-axis? No. Will an exponential graph hit an x-axis? Yes, if it were to like be moved down, or it has like a reflection, it could hit our x-axis. Okay, but this one does not have one. Our y-intercept would be at trace 0, enter on my calculator, if you remember the buttons that we hit to see that. This is a really nice y-intercept. Up at 0, 1. So before we move on, just reminders on how do I use my calculator to find that. X-intercept is your zeros. Second, calc, 0 option. A little bit left, a little bit right, enter to skip guess. Y-intercept, trace 0, enter. If you've forgotten either of those two things, write that down for yourself. All right, to the asymptote. The asymptote shows end behavior if your graph ever flatlines, and our graph is flatlining right here. We have a horizontal asymptote right here. The end behavior to the left is going to slide right along that asymptote. All exponential functions will have a horizontal asymptote. It will start at y equals 0, the horizontal line that runs along our x-axis, y equals 0. It will only ever change if my graph moves up or down. Okay, so if with the transformation, and we're going to talk transformations today, if my graph moves up or down, it will impact my horizontal asymptote. Bless you. But that's the only time it's going to change. It will not be impacted if my graph moves right or left because the horizontal line stays the same place if it moves right or left. If it's a stretch or shrink, if it's an ROX or an ROY, that will not change my asymptote. The only thing that will change it is a up or down movement of my graph. Your end behavior. This one is a little bit different too because we are used to them kind of matching on both sides. But in an exponential graph, they will not match on both sides. If we look at this function on the left-hand side, our graph is flatlining at the horizontal asymptote, so flatlining at 0, right? But on the right-hand side, where is our graph headed? As I follow the right-hand side of my graph, it's going up, right? So the right-hand side of my graph's end behavior is infinity. Now, one thing I want to point out, is it coincidence that that matches my range? No. The order does not have to match. Don't get me wrong on that. The order does not have to match, but there is a direct tie between your range and your end behavior. One side should be one part of your range, the other side should match the other part of your range. Always, okay? And then the last part, increasing or decreasing. When it is an exponential function, it will do one or the other of those the entire time. What's this graph doing? Increasing. This entire graph is increasing the entire time, never decreasing. It can only do one or the other the entire time. Any questions on that? All right. Give you a second to work on this next one ahead of me. F of x equals 5 to the negative x minus 2. And then we will talk answers. We'll do one or the other. So it'll either always be increasing or always be decreasing. You will not. You will not. The only type of asymptote we'll ever have. Now you will be asked that today, if it will be a vertical, a horizontal, or a slant. Exponential will always only be horizontal. I about said the wrong word. Horizontal. No vertical, no slant, ever. You should notice a very similar shape to the one we just saw, but going the other way. Which hopefully is going the other way, if you got the negative in there. Okay, and we'll talk about why it's going the other way because of that negative. Okay, one thing your calculator will never ever graph vertical or horizontal or any direction is an asymptote, but this does have an asymptote. And you can see it happening in your picture, but you don't actually see the asymptote, but it is running right here at -2. And do you see how your graph kind of came up to -2 and then flatlined? Okay, that's because it's coming up to that horizontal asymptote and flatlining right there. Okay, why do we have a horizontal asymptote at -2 on this one? Because our graph moved down 2, so our asymptote moved down 2. And we're going to talk more about the transformation side of it in just a minute. But I know that my asymptote did move down 2. Again, didn't have to draw that part of it, but I want you to know that that's what's happening in your picture. Okay, domain on this, always unrestricted, right? Always -infinity to infinity for an exponential, no matter what transformations are happening. Okay, now let's talk about the rest of it. The range, what is the lowest point this is going to get close to? -2, right? That asymptote, -2. And then we've got on the other side an arrow pointing up forever. So the highest this graph would ever go is up to +infinity. Your calculator has to find your intercepts for you. So take a second and remind yourself, how do you find the intercepts? Using your calculator. This arrow is 2 ways, always, because it's kind of slanty. Yep, so left forever. Okay. X-intercept was not a pretty one, was it? -0.4, yeah. Y-intercept I think turned out nice, right? 0, -1. Okay. And then moving down to our end behavior. Your end behavior should look like your range, one on one side, one on the other. As we look at this picture, the left-hand side is the one that, left-hand side is the one that is going up to infinity. Your right-hand side was the one that is headed towards -2. Is our graph increasing or decreasing the whole time? Decreasing. Never increasing on this one. Okay, so why the difference in our pictures, and how can I predict or know whether it was increasing or decreasing, whether it's kind of this one heading downhill or the one that we just saw that was heading up as we head to the right? This is taken out of your book, and actually the words they use for it is exponential growth and exponential decay. And where does it come from? Well, it comes from the number, the base number that's being raised to your exponent. If the base is a big number, bigger than 1, it's going to exponentially grow. Okay? If your base is a fraction, it is going to be exponential decay. But on that last one, wasn't our base 5? It absolutely was 5. So why did that one look like exponential decay? Well, the other thing that can make it look like a fraction is when you have a negative exponent. Why does that make it look like a fraction? 5 to the -1 would actually be 1 over 5, right? The negative is what drops it to the bottom and is actually making it into a fraction, the exponential decay. So either a fraction base or a negative exponent is what's going to make it look like exponential decay. I show you this out of the book so you can kind of see that and see their words, not really changing what we do on that. Any questions? All right, we're done with the graphing calculator part, onto the non-calculator part. Okay, so one thing we need to do is remind ourselves of transformations. We haven't talked transformations in a while. We are doing a lot of transformations this chapter with our exponential and logarithmic graphs. One of the things I might suggest that you find somewhere in your notes is we had this beautiful cheat sheet that had all of the different transformations, the ROX, ROY, vertical stretch. You remember all of those, right? Coming back in today for the rest of the semester and next semester. So take a second. Up there are 4 transformations in that equation right there. I want you to talk to your table partner, or if you don't have a table partner, to people around you, And I'm going to give you guys about 30 seconds here, and then I'm going to pick on people to give me answers about each of those transformations. What are they? What are their vocab words? All of that. So take a second to talk about them. You think you got it? You guys are giving me all the answers for the rest of today. So I'll give you time to talk to your table partners, but be ready to be called on for any of these. And there's not a lot of you in here, so you guys are all going to get multiple chances to answers today. Okay? Jonathan, since you got it, start with that first one. What's the negative called or do? Okay, before we move on from that one, if I were looking at a table of values, which column would I change for an ROX? Y column, the Y column. Very good. Let's go, Alana, how about the 2? Multiplication on the outside of our function. Somebody give her one word. Vertical. I like that word. It's a good word. It's a good word. Vertical. Okay. Alex Downing, she would like to phone a friend. Vertical what? By? Good. Okay. Let's move to the inside of that one. Cool, Gideon, tell me about the -3. Right 3. Cole, you got lots of help today. Okay. McGuire, tell me about the +5. Up 5. Guys, I am going to highlight anything that ever has the word up or down anytime we are doing exponential because it will also impact, does anyone remember? The asymptote and the range. Together, yes, both of which it will impact. So it's very important to look for those words up or down. Okay, if you have not already, you've got about 10 seconds to talk to your table partner now about that second one. All right, Kaylin, tell me about the negative. Seth, tell me about the 2. Horizontal, good word to start with. Yeah? Good. By reciprocal, notice it's opposite of what we see. Remember, everything inside is opposite of what we see, okay? Remembering your transformations is going to be very big for this. So go back, find that cheat sheet, come in and get help, whatever it is. One of the other things is, as you look at that sheet, you'll remember that on one of the other sides, we've made up all of our tables of favorite points. Guys, there is not one set table of favorite points for an exponential graph, okay? But once we figure out that table, we have to change the X and Y column based on what's inside and outside. So let's talk about what's inside and outside of your function, or where those are located. In an exponential function, if you are ever going to call something inside the function, it has to literally be written in the exponent, okay? So inside would be anything written up here. Things that can be written up there would be a negative for an ROY, a multiplication on that X for a horizontal shrink or stretch, a plus or minus would move us right or left. So remembering all the things that can happen up there, okay? If it is going to be outside of our function, it would be something sitting in front of the 5 would be considered outside. Typically, but not limited to, you would see a negative for an ROX there, or you would see another number, usually then the 5 would be in parentheses, and that would be for a vertical shrink or stretch. And typically, but not limited to, something behind it would also be considered outside. That is usually where you have your up or down with a plus or a minus something, okay? I say typically because technically we could move a plus or a minus in front of it and it would still be considered outside. Remember, anything is outside if it is not up in the exponent. Now, one thing I want to point out is you always have to have a base number for an exponential equation, right? And in this case, that would be the 5. The base number is not a transformation. The base number is what we will use. So in this case, this is our base, okay? And the base is not a transformation. It is the number we use to create our table of points. Our favorite points for each of those adjust specific to the number that is the base of that. So we use to make the table. And I'll show you how to do that in just a minute, okay? But just to be, some people want the 5 to be a transformation. It is not a transformation. It's the number we use to make our table of points. So there's 2 equations. Here's your 30 seconds to talk with your table partner about what each of those transformations are doing. And then I will get those from you in just a minute. All right, let's go ahead and talk about our transformations that are in this. Sailor, tell me about the transformation in the first one. Okay. What bothers people about exponential functions is that we are not talking about the 1/3 right now. The 1/3 is not a transformation. There is only one transformation in that first equation, left 4. That is it. The base of the exponent is not a number you should talk about. That is the number you use to make your table, and you're done with it. Okay? So as we look at this one, the base of my exponent would be the 3. That is not a transformation. That is what I use to make my table, and you are done with it. Okay? Everything else is a transformation. So let's get the rest of those transformations up there. Seth, tell me about the negative here. Good. Nick Wageman, tell me about the 1/2. You're on the right track. It's vertical. Absolutely. Jared, help him out. Very good. Outside things are exactly what we see, guys. So it will shrink by 1/2. Vertical things impact our Y column, right? Jude, tell me about the -1. Good. Nick Peterson, tell me about the +5. Very good. And if it is moving up 5, what else is moving up 5? The range and the asymptote. You got it. Very good. Okay, so let's talk about how do we actually graph an exponential function. Job number 1 is learning how to create your table of favorite points. Now, it is going to adjust for every base that we work with. In this case, our base is 1/2. So if you think about the parent function on this one, take away any other transformation, because we'll just apply transformations like we used to, okay? The base is 1/2 to the x. So we're going to use 1/2 to fill in our table of favorite points. And so I'm going to go the long route here, and then we're going to speed it up. If I were to plug -1 into the function, it would be 1/2 to the -1. Which would be like 1 to the -1 over 2 to the -1, right? I would give that to both numbers in that fraction. And if it's a negative exponent, it really wants to go to the other part of the fraction, so the 1 would go down there and the 2 would go up there. I'm just plugging -1 into our function here. But we're not doing, that's a transformation. This is actually going to move our graph left 1. Back to transformations, right? We're just looking at the parent function. 1/2 to the x. It'll always be whatever the base number is to the x. Yep, so take out any other distractions there. Okay, so back to this, moving each of those. Okay, guys, all I did was took my fraction and moved it to the other part. What's the math word for doing that? Reciprocal, right? So when I raise something to the -1, the answer is the reciprocal. Always. So in your table, when I have a -1 here, the y value will always be the reciprocal of the base. Okay? How about when I raise something to the 0? Right? Anything, it doesn't matter what the base is. When I raise it to the 0, it will be 1. So 1 always. Okay? And when I raise something to the first, it stays the exact same. So in our table, when I raise it to the first, that should be whatever your base is. And again, remember guys, we are applying the transformations outside of this table of points. So I'm literally just taking the base number raised to the x and using the base to fill in my table. Any other value, negative, multiplication, add or subtract that is in there, we will then go through using our transformation process. ROX, ROY, multiply my x or y column, shrink or stretch, all of that stuff just like we used to. Okay? So in this one, we only have one thing, and that is to move our points left 1. In our transformation process, which is left 1, did I say the word up or down? I did not, which means our asymptote is not going to move. You're probably always going to want to draw that asymptote in there. It is not a requirement, but I will tell you people are a lot more successful if you do, because if you go past it, you've drawn the wrong graph. So draw your asymptote, identify your asymptote. Horizontal asymptote at y equals 0. It didn't move because we didn't say the word up or down. Graph each of these points. I have not applied this transformation because I like to count that one in the graph. Okay, so I'm going to lightly dot out -1, 2, 0, 1, 1, 1/2, and move them each to the left 1. -1, 2, 0, 1, 1, 1/2. Move them each to the left 1 would be right here. Move that one to the left 1 would be right here. Move that one to the left 1, it would be right there. One side of my graph is going to head up to infinity. The other is going to flatline along my asymptote. Okay, kind of guided by what we were talking about earlier, let's talk about our domain and range. Michael, tell me about the domain of this one. Always -infinity to infinity, never restricted, right? Okay, Brogan, how about the range on this one? 0 to positive infinity, yep. You got it. Lowest point is 0, highest point is positive infinity. And remember, your range is only ever going to change if we move it up or down to where our asymptote is, or if our graph were to have an ROX and flip upside down, then it's going to also impact our range. Questions? Okay, I think we're going to get the hang of this. We are sticking with the same base for all of the rest of this first part, so we don't have to re-talk through this, but that's a good thing to help you guide what numbers show up in your table. Always the reciprocal, 1, and the base, okay? So I'm using the same base. We're still thinking of 1/2 to the x, but it's now got a negative and a +2, which are transformations we will apply to our table of values, okay? That table of values is exactly what we just talked about, right? -1 will be the reciprocal of the base. 0 is always 1. 1 is always whatever the base is. If you forget those guys, you can just go raise it to that number, and it'll fill that in for you, okay? And then let's talk about each of our transformations that we see up there. Jordan, tell me about the negative here. Let's start with the word inside or outside of our function. That's the two options. Which one would you like to pick? What do you think? It's in your exponent. In these type of graphs, inside. Anything in your exponent is inside in these graphs. Okay, so she is correct. Inside our function. Okay, Lily, if it's inside, is it an ROX or an ROY? Okay, Sydney, does an ROY impact our X or Y column? X. Inside things always impact our X column. So we are now going to apply the negative by going down your X column and changing all the signs. 0 doesn't have a sign, so I don't have to do anything about that. Okay. And then let's talk about the +2 at the end there. Cole, +2, what's it doing to our graph? Up 2. Alex Roberts, if we say that our graph's moving up 2, what else is moving up 2? Not only the dots, but the dots are going to move up 2. You got it. Our asymptote also moving up 2. And that's where I would start my drawing. Move the asymptote up 2. Instead of being at 0, anytime I use the word up or down, I'm going to go move that first and write that for myself. Y equals 2. It's a horizontal line moved up 2. Okay? Now, I need to still do that to each of the dots that are on my table. I have yet to move them up 2. So now I'm going to go lightly put out these dots and move them up 2. 1, 2, move up 2. 0, 1, then move it up 2, and -1.5, up 2. Okay. Dylan, tell me about the domain. Always, right? That one's never going to change for us. Jonathan, tell me about the range on this one. Very good. Adjusted. Remember that your range and your asymptote should match somehow. One or the other part of the range should match your asymptote. Any questions? All right. Last one with that same base. Same table of favorite points. Apply your transformations. Identify your information here. -2 times 1/2 to the x. All right, Kenzie, tell me about the negative. In which column are you going to multiply? Good. Ellie, tell me about the 2. Which column would you multiply? So going to go down our y column, multiply by 2, -2 times 2, -4, -2, -1. Did we say the word up or down? No. So our asymptote is not moving. Draw your asymptote at 0. I don't have any other transformations to apply, so I just need to put those dots out there. -1, -4, 0, -2. 1, -1. This one got flipped over my x-axis, right? That's what ROX means, reflection over your x-axis, which is why it's down here. And you need to slow down and think carefully about your range on this one. Sailor, tell me about the domain. Good? Okay. Jared, what do you think about the range? You got it. Good job. Questions? Okay. Now, this next part, keep in mind that these are no calculator problems. I am introducing you to a new number. and that number is E. Okay, and I know that E is not a number in our language system, but E is a number in math, like pi is a number in math, right? E is an irrational number, meaning it does not repeat and it does not stop. For our purposes in graphing, you need to know the approximation for E. E is approximately 2.7. That you are responsible to know. You don't need to know any of this. That is how it's calculated. We don't need to know that, okay? But if you think about putting these into a table of values, you need to, I can graph 2.7 a lot easier than I can graph E, okay? But I also need to know it's reciprocal. Grab your calculators. There is an E button. Actually, there's two E buttons. The first E button you will find is located above your divide sign. The second one is on the right-hand side, and that's where if I were to like raise E to an exponent, and by right-hand side I mean left-hand side, what I want you to type in your calculator is 1 divided by E. 1 divided by E. Negative infinity to 0. Lowest point first. What is 1 divided by E? Right? And we need to know approximately what it is. So it is approximately 0.4. Okay, you guys are responsible to know, to memorize two numbers. That E is approximately 2.7, and that its reciprocal, or 1 over E, is approximately 0.4. And I would totally just use the decimal approximation because it's a lot easier for me to graph than thinking about 1 over E is. Okay? So making our table of favorite points when the base is E. Remember that on your table of favorite points, it goes -1, 0, 1. For -1 is the reciprocal. Well, we just figured out what that is on the last page, and yes, I have to have it memorized. It is 0.4. To the 0 is always 1. That doesn't change whether it's E or just any number. And then E is approximately 2.7. Those two numbers you are responsible for. Okay? So now let's apply our transformations in this one. Let's look at our transformation in this one. Kaylin, tell me about the 3 in there. What's it doing? Alex Downing, which column will I multiply? Very good. And that's the only transformation in this one. So then I go graph. Did we say the words up or down? No. So our asymptote does not move, right? Until I say the words up or down, that asymptote stays right there at 0. Graph the point. Now these are all going to be very approximate. -1/3 0.4, so -1/3 0.4, somewhere in there. Okay, 0, 1, and then 1/3, 2.7, somewhere up there. It's going to slide along my asymptote and then get really big really fast. Okay, Brogan, tell me about the domain. Good. Kenzie, how about our range? Ooh, I disagree. 0 to infinity, yeah. We're not going to cross that horizontal asymptote on this one, so it's only going to get close to but never get to 0. Any questions? All right, you guys work ahead of me on this last one. See if you remember. Try not to look back at the last one. See if you remember those numbers without looking back at it. It does say e to the negative x. That negative is kind of light up there. E to the negative x minus 1. Again, not a calculator problem. All right, Dylan, how about you fill in my y column for me? What are my numbers I'm missing here? Good. Nick Wageman, tell me about the negative. What column are you going to change? Always inside changes our x, or opposite letter for your ROX, ROY, right? Let's go. Jonathan, tell me about the -1. Michael, what does that tell me also to do? Agreed. Our points are going to move down 1. What also moves down 1? The asymptote. Okay. And then graph each of those. Let's see, 1.4, move them down 1, right? So 1.4 would have been here, moved down 1 is going to be approximately there. 0, 1 would have been here, moved down 1. -1, 2.7 would have been here, moved down 1. Lily, tell me about my domain. Good. Seth, how about our range? Good. Any questions? When you guys get to your worksheet today, the first couple that look like this that have the empty box there, remember that is graphing calculator stuff. So you are just drawing me a picture of what you see on your graphing calculator, telling me about these things. Some of them are going to go really fast, like these questions in the middle ask you about the asymptotes. What's the only type of asymptote an exponential graph has? Horizontal. So really fast answers in here, right? When you get to the back page, that is non-calculator. That is you using tables to graph.